Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about Weil's insight, where he linked the notion of topology with the problem of counting points over finite fields. And the key to this is the Frobenius morphism. If this is something that's not familiar to you, you might want to have a look at my video on finite fields via Galois theory. But here's a quick summary of what we need to know for this video. So we start here with P, a prime number. And what's very, very interesting is that if you have a field of characteristic P, the one we'll look at here is this algebraic closure of Fp, so denoted with Fp and the bar here. Then there is a field automorphism from Fp bar to Fp bar, which just basically takes a number alpha and raises it to the pth power. Okay, so this is clearly multiplicative, and the key is that because this is characteristic P, it's also additive. The thing that's going to be really important for us, though, is the following fact. Okay, so inside this Fp bar, there's a unique copy of the finite field with p to the n elements, and we can extract it in the following way. Okay, so alpha, an element of Fp bar, is going to be in this subfield which contains p to the n elements, this unique subfield with p to the n elements, if and only if it's the fixed point of the nth power of the Frobenius. So if you apply the nth power of the Frobenius to alpha, so that means that this here is going to be alpha to the p to the n, that equals alpha. So there's a set of all those alphas, okay, the p to the n of them is going to be this subfield here, okay. So now we want to apply this to projective varieties. Suppose now that you have x is going to be a projective variety inside p to the n, and we'll work here over the algebraic closure of Fp. And suppose it's defined by these polynomials f1 up to fr, and you can assume that the coefficients of this f1 up to fr are in some finite field, okay? And that finite field, you might as well call it fq, where q is p to the n, okay? So that's what you have here, and this n is this capital N over there, so that's a different n. Okay. So what you can do is that, of course, this p to the n consists of homogeneous coordinates, x0 up to xn. So you can apply this polynomial, this raising to the pth power, or this Frobenius automorphism to each of the entries. And in fact, we can apply powers of that too. So we have an nth power of the Frobenius acting on this projective space here. It takes the point with homogeneous coordinates x0 up to xn to, you just apply the nth power of the Frobenius to each of these coordinates. So that takes x0 up to xn to x0 to the p to the n, all the way up to xn to the p to the n. And then just as in this case here, what are the fixed points with respect to Frobenius to the n? For these to be equal, what you'll need is that you can see is that each of these points will actually be fixed. So firstly, this Frobenius, it will restrict to this Frobenius to the n will restrict to x. Okay, so why is that? And that's because Frobenius to the n is going to be the identity and all the coefficients of f1 up to fr. So that's why Frobenius to the n will be take x back to itself, and if you look at the fq rational points of x, that's just x, the fixed points of x with respect to the Frobenius to the n. Okay, so basically this setup shows that if you want to count the rational points of x, okay, one way to do that is to just count the number of fixed points with respect to this power of the Frobenius. So then you might ask, well, you want to know what this is, right? What that number. So are there formulas for counting the number of fixed points? And the interesting thing is that if you work in topology, then you might be very familiar with the following formula. and it uses the notion of cohomology. So I don't want to get into cohomology right now. I'll talk a little bit about that later. But this is what we need to know for right now. Okay, so what's cohomology about? So firstly, suppose you have J is some natural number. Then we have these contravariant functors. It's going to be Hj, and I'll look at coefficients inside Q. And these functors go from the category of topological spaces to the category of vector spaces. So in other words, it associates to any topological space, a vector space over Q. And then also, if you have any continuous map of topological spaces, you'll get a corresponding map on those vector spaces. Okay, so what's the formula for counting the number of fixed points? So this is the Lefschetz fixed point formula. And I'll state it in the following way. I'll look here at Y is some sort of smooth compact manifold, and the map F from Y to itself is going to be a smooth map, and we'll assume that it has a finite number of fixed points, and all of these are non-degenerate. I'll define what non-degenerate is in a little while. Okay, so if we're in this context here, so it looks a bit similar to what we have here. Here F, so here we have a map from something to itself, and it restricts to a map from X to X. So we have some sort of continuous map from a geometric object back to itself. Okay, we're going to define the Lefschetz number in this case. So let's see what it is. It's a bit of a complicated formula, and it's given as following. It's L of F. It depends on this map F, and it's given by this formula. So let's just try to parse what this formula is saying. So firstly, we have this Y, that was our smooth compact manifold, and in particular topological space. So this HJYQ gives you a vector space over Q. Now this is a contravariant functor, okay? So if you have a continuous map, you get a corresponding linear map. So here you'll get a linear map from HJYQ back to itself. And since this is a linear endomorphism, you can take its trace, and that'll be just some number. It'll be just some rational number. Okay, so you have this trace. And what you're going to do is you're going to look at all these traces for each of these J's, and there's going to be a finite number of them for which these are non-zero. Okay, only a finite number. And also these will be finite dimensional vector spaces. That comes from the compactness of the manifold. Okay, so in this case here, what you will find is you can look at the alternating sum of these, and that's defined to be the Lefschetz number. And the key point is that this is strongly related to the number of fixed points as follows. This is the theorem. This L of F is equal to the sum over all the fixed points, all the Y inside the fixed point set of F, of the indices of F at Y. And what is this index of F at Y? This is either plus or minus 1. Okay, that's all it can be. Okay, so when is it plus 1 and when is it minus 1? So what you can do is, well, you have this map F, right? And it sends Y to itself. Okay, it sends Y to itself. That's a fixed point. So it sends the tangent space back to itself. Okay, and that's the Jacobian. Okay, Jacobian map. So that's the derivative. Okay, it will map the tangent space at Y back to the tangent space at Y. Okay, so this is going to be some linear endomorphism. So you can subtract the identity and look at the determinant of that. Being a non-degenerate fixed point just means that this determinant is non-zero. Okay, and so you can talk about its sign. It's either plus 1 or minus 1. And that gives you the index. So adding up these plus 1s and minus 1s gives you the Lefschetz number. Okay, so this gives you quite some strong control over the number of fixed points. So in particular, if L of F is non-zero, there has to be at least one fixed point. Okay, so that's one classic use of this Lefschetz, what's called the Lefschetz fixed point formula. Okay, so what was Weil's insight? Okay, so Weil said, okay, let's just pretend that this works for F equals the nth power of the Frobenius. Okay, so let's, for this to work, of course, you have to have some sort of definition for the cohomology. Okay, so it's going to work for this map, okay, and for some cohomology theory. Okay, and we'll just denote it HJX. Okay, and he also thought that, well, in this case, well, if you just look at the Frobenius map, and if you want to try to pretend it's like in this situation here of a map between smooth manifolds, you'd probably expect that the index of f at y for this nth power of the Frobenius should equal +1. And that's the type of thing that you would expect. And let's just apply the formula and see what we get. Okay, so we'll apply the formula. Okay, so what's that? So I'm going to let nu n denote the number of fixed points of the nth power of the Frobenius. So that's the fpn rational points of x. That's what we've discussed here, right? Okay, that's what we have here. And now we just apply this formula, okay, for what this is. Okay, so that's just the Lefschetz number since all of these are ones. Okay, since all these are ones, you're just counting up the number of fixed points. So here what you have is you're going to look at the sum of -1 to the j of the fixed points of, there's a mistake here, let's fix that. And here, these are just the, you look at the Frobenius to the n. Okay, that'll give you a map from hjx to hjx. So you apply this with f equals Frobenius to the n. Okay, and that's what you have here. And the same should happen here. Okay, so we'll do that. Okay. So let's remind ourselves what the zeta function of this x is. Okay, so by definition, it's as follows. You look at these point counts, okay, as n increases. So for all positive integers n, that gives you these nu n's, and you form this power series. The coefficient of t to the n is nu n on n. Look at this power series, you exponentiate that, okay? And that's the definition of the zeta function for x. As we've written it here, this version of the zeta function. And now we have a formula for these coefficients nu n. It's given by this alternating sum. So whenever we see nu n, we can put this long alternating sum inside here. So you have an alternating sum. So this sum, of course, this alternating sum, you can pull out the sum, and exponentials take sums to products. So when you pull out that sum over all these j's, this alternating sum over j, now becomes an alternating product over j. So you have a product over j, okay, and it's alternating, so we're going to multiply by powers, and the power is going to be -1 to the j. Okay, so we pulled that out. And then you have to exponentiate everything else that's left, okay, for each of the j's. Okay, so let's see what's happening for each of the j's. You have a sum from n equals 1 to infinity, and this is the term you have. You have trace of the nth power of the Frobenius of on hjx. Okay, so that's my notation for the trace of the nth power of the Frobenius, and we're thinking of it as acting on this hj of x. And that was the value of nu n. So you still have the t to the n and on n here, t to the n on n. And that's what we have here. Okay, so one of the things that Weil conjectured is that this here should be some rational function of zx, of t rather. Okay, so this should be a rational function of t. And what we see here is that, well, this is an alternating product of the j, and the number of j's that should occur is finite. So if we can show that each of these exponential terms is going to be some sort of a rational function, we will be done. And that will follow from this lovely little proposition here, okay? So what type of quantity is this, okay? So it looks a little bit bizarre, but at the end of the day, what you have is you have a vector space hjx. So we'll apply this in the case where V is a vector space over Q, okay? The Frobenius to the n, that's just some endomorphism. Okay, so we'll look at the case Frobenius and n equals 1. So we'll just, f will be the Frobenius, that's what we want to apply it to. F from V to V is a linear map. Then let's have a look at this expression in this more general sort of setup. So basically, you've got some map here, which I'm going to call f, this linear map f, and you just look at all powers of that, f to the n. Okay, and you're going to look at the traces of those powers of f, and you're going to use those as the coefficients of t to the n on n, and form this power series and exponentiate that. And I claim that you can write this very succinctly as the determinant of 1 minus ft inverse. Okay, so if you look at what this is, Okay, essentially this is clearly a rational function. In fact, it's the inverse of a polynomial. Okay, so what's 1 minus ft? Okay, so here this is just a linear endomorphism. So of course, this is like the type of thing you get when you look at the characteristic polynomial. Okay, so and then you invert that. Okay, so let's see why this is true, and just remember, once we've established that, that will tell you that each of these terms, okay, will be the inverse of a polynomial. So this will be a rational function. This alternating product would indeed be a rational function. And in fact, it will also tell you ways to try to get a handle on what this is. Okay, in particular, this will factorize. This will factorize according to these HJXs, okay, these cohomology groups. And the exact nature depends on all these trace calculations. Okay, so let's see why this is true. And this is a lovely little calculation just involving some elementary linear algebra. I really like this, okay? So to compute the trace, the easiest way to do that is to upper triangularize this F over some algebraically closed field containing the field of interest. So let's suppose we go to the algebraic closure of Q, okay, and we let the eigenvalues of F be alpha 1 up to alpha d. Okay, so we assume that this is a d-dimensional vector space. Okay, and we just upper triangularize so that the diagonal entries will be alpha 1 up to alpha d, the eigenvalues of F. Okay. Then let's have a look at the left-hand side and see what happens here. So of course you have the exponential, you have the sum from n equals 1 up to infinity. And the t to the n on n, we'll leave that there. And the thing that we want to now look at is we want to compute the traces of this f to the n. So if we upper triangularize so that alpha 1 up to alpha d are the diagonal entries of f, then the diagonal entries of f to the n are just the nth powers of alpha 1 up to alpha d, and it's still upper triangularizable. So the trace of this f to the n is just the sum over from I equals 1 up to d of alpha I to the n. And that's something that we can put there straight away. Okay, so that's the first thing that we have. And then the key point is that if you look at this expression here, that's rather nice, okay? On the numerator, you can essentially see just the nth power of alpha I times t. That's divided by n, and you're summing that. And of course, we should recognize this as a well-known power series. It's just the negative of the natural logarithm of 1 minus alpha I t. So now what do? We take this sum and we pull it out so that instead of a sum here, we'll get a product. So it's a product from I equals 1 up to d. And what we've taken is the exponential of this inside term. The minus 1 gives you the inverse, and the exponential of the log just gives you this term here, 1 minus alpha I t. Okay, so here you have this product of these inverses. So we can pull the inverse out. Here's the inverse. And what is this term here? Well, if you diagonalize this f, or rather upper triangularize this f, and then you look at its diagonals are alpha 1 up to alpha d. So you can also upper triangularize 1 minus ft so that it has 1 minus alpha I t on the diagonals and is upper triangular. And of course, the determinant is just this product here. So this here is just the right-hand side. And hence, we've established this little proposition from linear algebra, which tells us that, yes, if you assume that there is some sort of Lefschetz fixed point formula that works in this setting here, or some nice cohomology theory, then you will get the first part of Weil's conjecture, which is the rationality of this zeta function. And what's more, they made some extra predictions as well. He also thought that they not only should have this cohomology theory, but this cohomology theory should behave a lot like the usual cohomology theory if you look at x, but not at the points over some finite field like this, but if you look at the complex points of this. Naturally, this was a very, very bold sort of a conjecture, and it prompted a lot of people to look for such a cohomology theory. And eventually this cohomology theory was found by Grothendieck. It's the L-adic cohomology, and it uses the étale topology. And he proved many wonderful facts about it, and using that, he proved most of Weil's conjectures, and the rest of the Weil conjectures were proved by Deligne. I hope you enjoyed this adventure in pure mathematics.